Welcome. In this session, we'll explore something in linear algebra that's called a one-form. Our motivation is something that we often see in multivariate calculus, and we want to formulate this in a way that's easy for us to manage. The idea is if we have a function that has a vector argument and produces a real number, and we have some vector that is in the domain of that function, a frequently encountered, so a frequent summation is this. We'll often see the partial derivative of the function with respect to the first variable times the first entry of the vector v, plus the partial derivative of the function with respect to the second variable times the second entry of v, and so on until we have represented all of the variables of the function and all of the entries of the vector. We could write that as a summation. We could say that's the sum as j goes from 1 to n of the partial derivative of f with respect to the jth variable times the jth entry of the vector that we're given. This arises, as I said, often, and one place that it arises, for example, is in neural networks. We're going to see this, and our question is, how could we write that summation in a concise way? Well, one way we could do that is we could say, well, this looks like a dot product. So what we could do is we could write this as the partial derivative of the function with respect to w1, with respect to w2, and so on until we get the partial derivative of the function with respect to the nth variable. And we could say that that's the dot product with v. Or we could write that as v dot and that same long vector. And many authors will do this. Many sources that you'll see will represent, they'll take the partial derivatives and they'll stack them up into a conventional vector, and then they'll take a dot product. We can see, though, that there's another way that we could write this. So let's consider an idea from linear algebra. So consider, we'll say, from linear algebra, a one-form. And a one-form is, we will write this as, let's say it's a one-form A. If A was a vector, we would put an arrow on top. And my personal notation is, I'll take the same symbol and I'll put an underline. And this is something that I do. It's not something that most authors will do. I will define a one-form as something with a bar underneath it. And I will say that that equals, by definition, A1, A2, and so on until we have expressed all of the possible entries. Let's observe that if a vector is written as a column and strictly as a column matrix, we can say then a one-form is a row type matrix. That is, there's nothing, when we write this, we actually can't tell whether it's intended to be a one-form or whether it's intended to be a matrix that has only one row. So what we'll do again, this is, so now we're going to say, we're going to assume that the underlying vector space has a Euclidean geometry. What we'll do is we will say that if A is a vector and we take the transpose of that, that's the same as a 1 form, and that if we take a 1 form and we transpose that, that we would get a vector representation. These are appropriate if the underlying vector space, if this vector space over here has a Euclidean geometry, then this works. If it doesn't have a Euclidean geometry, then we have some other terms that get involved in addition to this simple transposition. If you read further on this, a 1 form will sometimes be defined as a dual vector. It will sometimes be defined as a covariant vector. There are lots of different ways to do it. What we'll do is we're just going to call this a 1 form. So if we call it a 1 form, we can now write this summation as this. We can say that the sum, as j goes from 1 to n, of the partial derivative of a function with respect to variable j times the jth entry of a vector equals, we'll say that that is the partial derivative of the function with respect to 1, partial derivative with respect to variable 2, and so on, partial derivative of f with respect to the nth variable times v. And it's important that when we have a 1 form and we have a vector, that the way that matrix vector multiplication works is it will be producing exactly the same thing as this sum. So we could write this as a sum. Other authors will write it as a dot product. We will write it as a 1 form times this vector. And in the next session, we're going to give this a particular name, and we're going to start using it in some of our optimization.